So hello everyone, and welcome to our 19th web seminar of this series of Latin American webinars on physics. So my name is Nicolás Bernal, and I'm from the ICTP-SAIFR in Brazil, and I will be your host today. So today our speaker is Andreas Goudelis from the Institute of High Energy Physics in Vienna. We'll talk about BBN and the cosmic lithium problem. So Andreas got his PhD from LPT in Orsay in France. And after a couple of postdocs, first in DESI and the second in the Laboratoire Physique Théorique of ANSI, he moved to Vienna, where he's currently a postdoc working on dark matter and beyond standard model physics. So Andrea will talk today about, well, his title is A Light Particle Solution of the Cosmic Lithium Problem. And we are very glad to have him as our speaker today. But first, remind that you can be part of the discussion, writing questions and comments using our Google Plus Q&A system, so this one, and on Twitter with the hashtag LAWOP. So now I will hand you over, Andrea.
Okay, so thank you very much, Nicolás, and thank you very much for asking me to give this seminar. And let me just start by saying that, okay, this is the first time I'm giving a web seminar, so yeah, I hope this goes well, and I hope, yeah, everyone enjoys it. So that's it. I guess I should share my screen. Whoops. But yeah. What I'm going to discuss today is, as Nicolás said, the primordial nucleosynthesis, and in particular, the so-called Lithium-7 problem. I will explain what the Lithium-7 problem is in a little bit, and a new solution for the cosmic lithium problem that we proposed in this seminar, along with Maxim Pospelov and Josef Pradler. So, first of all, some general things about BBN, because not necessarily everyone is an expert on Big Bang nucleosynthesis. I wasn't one till a while ago, at least. So, Big Bang nucleosynthesis is, in general, the theoretical framework that explains qualitatively and, well, hopefully quantitatively, the formation and abundance of light elements in the universe. So, in its minimal form, Big Bang nucleosynthesis, called standard, so-called standard Big Bang nucleosynthesis, is basically a pretty standard assumptions, hence standard, which is that general relativity is valid, and basically on the particle and or nuclear physics side, you make just the assumption that the standard model of particle physics is valid, and that some standard nuclear physics is also valid, where by standard nuclear physics we basically mean a network of nuclear reactions that enters the way in which light elements form. So one very important point about standard Big Bang nucleosynthesis is that up to a few years ago, it contained just one free parameter, essentially, which is the so-called baryon to photon ratio, which is simply the ratio of abundances of baryons over the abundance of photons in the universe. But lately, well, since a bit more than 10 years, WMAP and Planck have actually measured the baryon to photon ratio to this value 6, roughly 10 to the minus 10. And since then, standard BBN basically becomes a closed theory, and it has no free parameters. So the very important and very interesting point about standard Big Bang nucleosynthesis is that it can actually be used to check the consistency of the main assumptions that SBBN contains, which again are GR, the standard model, and some nuclear physics assumptions. And so far, actually, standard Big Bang nucleosynthesis is doing an excellent job in predicting at least the very, very light, the abundance of very, very light elements in the universe. So you can see here a few, like 2 numbers. I'm only going to focus on these, on deuterium, helium, and lithium, lithium-7 in this talk. There's an interesting theory and interesting observations behind lithium-6 or helium-3 and tritium and so on. They are taken into account throughout the numerics, let's say, that follow, but I won't discuss them just to simplify things. And as you can see from these numbers, here on the left-hand side, we have the observed value of deuterium, for instance. And the right-hand side, we have the prediction of standard BBN, which I took from this paper. And you see an excellent agreement, actually. And you also see, again, on the left-hand side, that the deuterium abundance in the universe, and all of them are typically normalized to hydrogen, is actually measured to a very, very good accuracy of the order of at the percent level, basically. And the same applies actually to the helium abundance, which is measured also extremely well. And you see that the prediction of standard Big Bang nucleosynthesis is once again extremely successful with respect to observations. Now, there is one quite celebrated, actually, exception to how well standard BBN does. Over the history of BBN, there have been other discrepancies, even in deuterium and so on, but lately these have been resolved. The main discrepancy that persists is the prediction for the lithium abundance, where here you can see on top the observed abundance of lithium-7, and this value is inferred mostly from so-called population 2 stars. Population 2 stars are very old stars, which people think give a relatively precise determination of the primordial abundances of chemical elements, lithium-7 in this case. And on just underneath, you can see here the prediction of standard BBN theory. And you see basically that there is clearly a discrepancy of a factor 2 to 5, depending on how you count the uncertainties. And this has been dubbed the cosmological lithium problem. So this is what we will set off to try and solve in this talk, and we'll try to solve in the paper that I mentioned in the beginning. So there are many solutions that you can envisage, actually, in order to resolve this tension that exists. A first solution, so you're a theorist and you see that observations don't agree with your theory. What do? You blame the observations. That's the first type of solution, one could say. I mean, a bit more seriously, what happens is that you can actually argue that population 2 stars are not a good tracer of primordial lithium-7. So basically, that the abundance you infer from the atmospheres of population 2 stars does not correspond to the abundance, to the lithium abundance of primordial origin. This is actually turns out to be a little bit harder to realize than it sounds, because then you have to explain what happened to the lithium-7, and you have to find mechanisms inside these stars so as to destroy lithium. So the whole story is basically how do you destroy the primordial lithium, right? A second type of solutions, we could say, is that you can inject some photons. And whenever I say inject, typically what I mean, if you will, in a model-dependent framework, that somehow magically in the early universe you just assume that an extra population of photons comes in. And the same applies to every time I say inject this or inject that. And this is actually a solution that works. It has been, here I show just 2 example references which are relatively recent. So the second one in particular is very recent. And yeah, this type of solution works. The third type of solution is to inject so-called catalysts. So catalysts are basically charged particles beyond the standard model, massive particles beyond the standard model and charged, which form bound states with the nuclei in the early universe. So this has several actually consequences, among which that you modify the Coulomb barriers of certain types of nuclei, and secondly that you change some selection rules for nuclear reactions. So some reactions that were previously not possible either due to Coulomb blocking or due to quantum mechanical selection rules now might become possible, and you might be able to destroy helium through reactions that previously were just not effective, through which it wasn't possible to do it. And the last type of solutions is, there are others, but among those that I discuss is to inject extra neutrons. Now, injecting extra neutrons, we will discuss it a little bit in the next transparency. It is quite disfavored at this point, if not completely excluded, because it overproduces deuterium. So let's see what's the problem with extra neutrons. So the basic problem, first of all, neutron injection has been motivated by numerous GeV or TeV scale PSM scenarios. One of the most standard examples is supersymmetric scenarios with gravitino LSB, where you have some heavier supersymmetric particle decaying into the gravitino LSB plus hadrons, among which neutrons. And yeah, you can see some examples of this mechanism in this reference and the references therein. And in this case, lithium-7 depletion is actually achieved through this combination of reactions. So generically, by the way, one thing just to clarify is that lithium-7, please look at the left-hand side reaction written here. Lithium-7 is not produced as such that much in the early universe. Mostly it comes from beryllium-7, so in the following I will be mostly referring to beryllium-7, or I'll be referring interchangeably to beryllium-7 and lithium-7. They're basically the same thing as far as the purposes of this talk are concerned. But yeah, the main idea with extra neutrons is that you convert early enough beryllium to lithium-7, and then lithium-7, if you do things early enough, is broken up to two helium-4 nuclei. The point now is that if you inject neutrons in the early universe, they will also tend to just bind with protons and form deuterium. And as we saw, the abundance of deuterium has been measured really, really well by this point. And the prediction of standard BBN is actually in very, very good agreement with observations. So this basically creates a massive problem, which amounts to most solutions based on extra neutron injections to be excluded. And for some analysis of the constraints, you can see these two references. Now, one idea that one can entertain, and we've actually entertained in our paper, is that you can actually envisage a situation where you don't inject extra neutrons, but you try to instead use some of the ones that are floating around in the early universe, either by themselves or actually bound in other nuclei, and in particular bound in deuterium. So I will be saying much more on this borrowed neutron issue in what follows, but keep in mind that, yeah, in the early universe there are already quite a few neutrons. Many of them are bound in helium. You better not destroy helium because it's really hard to reform. And some others are bound in deuterium, and we will see what happens with deuterium, actually. So here are some points to remember, and the first point mainly repeats now I pass to our solution of the lithium problem, actually. So the first point to remember is what I said previously, that lithium-7 is mainly formed through this reaction, helium-3 plus helium-4 giving beryllium and a photon, and then beryllium goes to lithium by charge exchange, basically, with a neutron. The second point to remember is that the bulk of beryllium production takes place between 60 and 40 kiloelectron volt in the early universe, and this reaction is very, very slow. So this first reaction is very slow. And by the way, this is why there is so much little beryllium and hence lithium in the universe, because if you remember, there's really many orders of magnitude difference between the abundances of deuterium and helium and the abundance of lithium. At the same time, what is now really crucial is that helium-3, helium-4, and in particular deuterium formation remains fast. So the main idea of our main idea is the following: that you inject some particle X, which you can see here schematically, that breaks up beryllium into helium-3 plus helium-4, and it potentially also breaks up deuterium into a neutron and a proton. Then beryllium is destroyed by these X particles, but then you have also broken up deuterium. This has released neutrons, and this means that these neutrons are now available to break up beryllium themselves. So, and the most important thing is that since deuterium formation remains faster than the neutron decay lifetime, down to a temperature of 10 kiloelectron volt, then if the X particles are injected early enough, even if we destroy some deuterium, it can reform, and unlike beryllium. So I hope that the main idea is clear so far. You inject a species, once again, you inject the particle species X, it breaks up beryllium, and at the same time, it breaks up deuterium. and you allow this. It doesn't matter. And it doesn't matter because A, deuterium will reform, B, deuterium breakup actually helps you with the lithium-7 problem because the extra neutrons also break up beryllium. So, what are some general ingredients and requirements for the previous to work? The first thing is that, as we said, we need these two reactions, beryllium breakup and deuterium breakup. At the same time, however, you want to avoid the inverse of the first reaction, because then you get back where you started. So the important thing is to remember that the reaction rate is not just proportional to the cross-section, it is proportional to the cross-section times the abundance of a particle. So these conditions, having the forward reaction of beryllium and deuterium breakup, but not the inverse reaction, are actually quite easy to meet, as long as A, the X particles interact quite weakly. So basically, if you go again in the line above, this reaction is in principle small, and this is also in principle small, but then you can dial up the abundance of X particles and actually get a substantial reaction rate in this one, and this one, and this reaction, and a minuscule reaction rate in this process. So these are two basic requirements, and these are two basic guidelines for all of the analysis that follows. And a good starting point is basically to take X to have an abundance which is larger than the baryon abundance in the universe, and quite a bit smaller than the photon abundance in the universe. And this actually is given the fact that the baryon to photon ratio is 10 to the minus 10, you have really quite a bit of room to play, and you can see that the abundances and hence the cross sections can actually vary in a pretty large range. At the same time, of course, there is a kind of sine qua non condition, which is that you want to avoid helium-4 destruction. And this is just because helium-4 has such a large binding energy that it's actually very, very hard to reform. So just to avoid this process, one must basically choose that the mass, or if you will, the energy of the X particle, the particle will inject it, must be smaller than 20 MeV. So let's pass to see how let's go on to see how this whole thing works. So in these, as a first step, we work completely model independently, and we take a set of three parameters, which is the mass of the injected particle, its lifetime, its abundance, which we conventionally normalize over the baryon abundance, its cross-section against beryllium, and its cross-section against deuterium. Now, this parameterization, of course, might shock a little bit, because in any imaginable UV scenario, in any imaginable concrete particle physics model, the beryllium and the deuterium cross sections, as is written at the bottom of the page, are of course not independent parameters. But just in order to see if this whole idea makes any sense, we consider them at first as independent parameters and we vary them. And just as a remark, we assume that both cross sections are RS wave, so there is no velocity dependence, and this simplifies things quite a bit. And here, in the left and the right-hand side, I show two examples of playing this game of varying. In the y-axis, the cross-sections. So it's the y-axis is the cross-section for beryllium dissociation over the cross-section, of deuterium dissociation over the cross-section for beryllium dissociation. And in the x-axis, we have the cross-section against beryllium multiplied by the abundance of the X particle. And both plots show the same, are in the same plane. And the difference between the two plots is that in one case we assume that the X particle is completely stable, whereas in the right-hand side plot we assume that X has a lifetime which is comparable basically to the neutron lifetime, so 1,000 seconds. Now, as I said, there are two reactions that we consider. There is the reaction of deuterium dissociation, which then releases neutrons, which in turn break up beryllium. And there is, of course, the direct reaction, which is direct beryllium breakup, just this one, which I call R1 and R2. And in both plots, it's clear that in these plots, along the blue bands, the lithium-7 problem is solved. So you achieve an order a few order factor of a few reduction of the beryllium abundance. In this side of the band, I mean, this is quite obvious, but I'm explaining nonetheless. In this side of the band, and equivalently here, the lithium problem is solved mainly through this idea of this mechanism of borrowed neutrons. You basically break up deuterium, and the released neutrons break up beryllium. In the vertical side of the bands, the beryllium cross-section is quite large, and here you just have the direct reaction, the direct beryllium dissociation that is the main mechanism solving the lithium problem. Yeah, I guess that this is what I wanted to say in these plots. Oh, yes. No, there's another point which is actually very interesting. You will notice that here we have some constraints in this line and this line, and you will also notice that there is a strange effect that above this line, the dashed line, the deuterium abundance becomes too low, whereas above this line, the deuterium abundance becomes too high. So the problem so this is kind of a strange effect, but it can actually be understood. So if we focus on the left-hand side plot at first, which is the easiest to understand, is what happens above this line is that simply you break up so much deuterium that yeah, you end up with too little deuterium in the end, and this means that yeah, given the precise determination of the deuterium abundance, everything actually in this region is excluded. So in the infinite X lifetime scenario, you can basically only rely on direct beryllium destruction. In the right-hand side, with the finite lifetime, first of all, you see that everything is kind of shifted towards larger cross sections. What happens in this scenario is that you end up destroying deuterium actually, in this case, also you destroy too much deuterium. But the point is that you do it early. If you destroy too much deuterium too early, you end up with, so if you have too few deuterium at early times, you end up with too much deuterium at late times. And this is because helium is basically, helium-4 basically comes from deuterium plus deuterium giving helium. And so what happens is that as you have broken up deuterium, not enough deuterium binds into helium. And eventually deuterium does form, but at energies where helium can no longer form. So you end up with a lot of deuterium at late times floating around in the universe, and you just violate the upper bound on the deuterium abundance. Okay. So let's see now how all of this looks like a bit in action. Here we just here we plot as a function of the temperature the various elemental abundance evolution. So all of them are actually normalized to hydrogen, and you can see the helium abundance, the deuterium abundance, and the beryllium abundance, which will end up to lithium later on. And the blue line corresponds to the neutron abundance. So all dashed lines in this plot, so this one, and this one, show, if you will, the excuse me, but there seems to be some noise from outside. Yeah, all of the dashed lines show the kind of unperturbed BBN scenario. So this would be basically, the dashed lines show basically standard Big Bang nucleosynthesis, and the solid lines are the ones that we get in our scenario for a lifetime, as you can see here, of 1,000 seconds. This turns out to be the most favorable scenario in the end. And actually, in this whole picture, if you could actually read the numbers in beryllium plus lithium here, you would actually see that you end up with a correct abundance of lithium in the end. And in all of this plot, actually, whoops, excuse me, the dominant reaction is R2, where R2 was the borrowed neutron mechanism. Basically, what is dominating in this picture is the borrowed neutron mechanism. Okay. And yeah, you see the effect of borrowed neutrons. You can actually see it in this little region where it's written borrowed neutrons, that whereas the neutron abundance would follow the dashed line, this dotted line, actually, now you have a little bump, and then you return to the normal evolution. And at the same time, when you have this little bump, the beryllium abundance goes down, actually. Okay. You can also see a small change in the helium-3 plus tritium abundance, and but everything is okay basically in this plot. You solve the lithium problem, you don't violate any other bound from Big Bang nucleosynthesis, and so on. So yeah, and here you can just see what I have been saying, that lithium-7 can be reduced to its observed abundance. Now, let's start putting in some numbers in order to get an idea of what type of models could actually, with what type of models we could actually play this game. So from these pictures, we actually find out that if we take, again, the example of an X particle which is unstable with a lifetime that's comparable to the neutron lifetime, we find that reaction rates that lead to a solution of the lithium problem are of the ballpark of 10 to the minus 31 centimeters square for direct beryllium destruction, and a little bit higher for, or actually a little bit higher in the case of deuterium dissociation. And then just to put in again some numbers, if we take the mass of the X particle or its energy, and at this case I must clarify that I say mass or energy because you get the same effect with a non-relativistic particle, which has, say, a mass of, in this case, 5 MeV, or with a massless particle, which is relativistic and which has an energy of 5 MeV. It basically doesn't matter as long as you have enough energy, either in the form of kinetic energy or in the form of mass energy, so as to break up beryllium and deuterium. You're okay. You have the same result. And so take a mass or energy of 5 MeV and the X particles to contribute around 1% of the photon energy density at the temperature of 50 kiloelectron volt. Then you end up with a cross-section of the order of 10 to the minus 38 centimeters square. And if you compare this to other types of reaction, this is actually a much smaller cross-section than the cross-sections which occur typically in photonuclear reactions, and it's much larger than weak-scale cross-sections. Of course, this is just, I mean, this is not the only value of cross-section for which you can get a solution to the lithium problem, because remember that the abundance can vary in a really large range, and this means that the cross-section can also vary in a pretty large range. This is just a ballpark number in order to start considering what types of models we could imagine. So, as a proof of principle, we actually considered two types of models, two scenarios. What we could call so in both cases we take the X particle to be an axion-like particle, so it's just a pseudoscalar essentially with a derivative interaction. And we have two scenarios, the so-called heavy axion-like particle scenario and the light axion-like particle scenario. So in the heavy ALP scenario, I mean, the ALP is not that heavy, actually. It depends on what you compare it to. So X, or we'll be calling it A, is non-relativistic. It has a mass of roughly 1.6 to 20 MeV, where the upper bound comes from the requirement not to destroy helium-4, and the lower bound comes simply from the fact that you want nonetheless to be above the beryllium-7 binding energy. And then we assume a very simple Lagrangian. It's actually kind of a toy Lagrangian, if you will, where you have an axion-like particle A that couples only to the down quarks through a derivative interaction. And you will note that we have actually suppressed the couplings to up quarks. This is simply due to the fact that we wanted to avoid flavor-changing kaon and B meson decays, because there are extremely strong bounds on that. And so, yeah, in this scenario, basically, X breaks up, the X particle or A particle breaks up deuterium and beryllium, and then decays into either standard model particles. I mean, it will decay in any case into standard model particles, or even some beyond the standard model particle radiation that eventually redshifts away. Okay. Now, this scenario turns out to be actually a little bit tricky, since the axion-like particle is expected to be populated quite a bit during the QCD epoch. This means that you end up with quite large abundances at the beginning of BBN, and it actually might start posing a problem at some point. So according to what we found, at least, we probably need the A particle to annihilate away into some beyond standard model type of probably radiation. You can imagine many scenarios. You can also imagine 3-to-2 reactions in order to reduce the abundance of the axion-like particle. In any case, yeah, this scenario works as far as BBN is concerned, but if you actually try to implement it a little bit realistically, it's a little bit more tricky. You need some extra, if you will, you need to freeze out quite efficiently the abundance of A in order to end up with the right abundance in the beginning of BBN. So the most easy to implement is actually the scenario B of the light axion-like particle. So in this scenario, you have an energetic, almost massless particle X, which arises from the decay of a massive progenitor particle XP. And then you take the mass of XP to be twice the energy that you need for the X particle in order to break up beryllium and deuterium. And so, yeah, that's the general mechanism. Now, where does XP come from? Actually, this is the easy part. You can simply assume a freeze-in scenario and freeze in XP through this Higgs, through the standard model Higgs boson, essentially. And then XP will pair decay through such a term to a pair of axion-like particles. And then you, of course, add the same Lagrangian as before in order to do the job that you want, that is to break up beryllium. Then, as previously, the rest of the scenario goes a little bit as previously. X breaks up deuterium and beryllium. And one difference is that you actually, in this case, A actually redshifts away. If its mass is extremely small, it almost behaves as radiation. And as the universe expands, its energy goes down, so you're okay. And you actually don't even have a problem from previous creation of the axion-like particle, because by the time of BBN, any previous population has actually decayed away. So all you need to do is to dial the abundance of the parent particle at the beginning of BBN and make XP decay to the A particles. Yeah, and this scenario actually is quite easy to realize. And we have, now concrete model building, more sophisticated model buildings examples are actually under construction at this moment. So let's, before we, I think I'm approaching the end actually of the talk. So as a final example, let's show how scenario B actually works in practice. So we fix the parent particle abundance, and we determined the coupling of X and the axion-like particle that actually breaks up beryllium and deuterium, and the lifetime of the parent particle, for which we can actually solve the lithium-7 problem. So here we have fixed the abundance to 3 × 10⁴ with respect to the baryon abundance. We have taken a mass of the parent particle to be of the order of 10 MeV. And we plot what is the suppression scale, because remember, I'm going a little bit to the previous slide. Here you have this mass suppression scale, which we plot in the y-axis. And we plot it against the lifetime of the parent particle. And again, as previously, the blue band is where the lithium problem is actually solved. And you see that there is actually quite a big range of FD scales and parent particle lifetimes for which you can actually solve very nicely the lithium problem. There are some constraints. In one case, as before, the deuterium abundance turns out to be too high. In the other case, it turns out to be too low. So this mechanism basically provides a fully viable solution for the lithium problem. As a bonus in this scenario, keep in mind one thing, that this line is not fixed. If we change the abundance of the X particle, then this band is going to move upwards or downwards depending on whether you reduce or you increase, or you reduce the abundance of the parent particle. So as an additional bonus, actually, in this scenario, we have calculated, if you will, a ballpark rate of events in some LS&D type experiments, and we actually find that if this FD scale is of the order of 1 TeV, you can actually have pretty good perspectives for detection of the axion-like particles in LS&D-like experiments. So yeah, the idea is basically that you have protons hitting nuclei, and then you produce this A particle, and then you observe this this A particle through its decay. So I've already reached basically the end of my presentation. Yeah, I was told to speak, I think, more or less for this time. So we have proposed a new solution to the cosmological lithium problem, which is based on new electromagnetically neutral light particles that interact non-negligibly with nucleons. We pointed out that even if we momentarily decrease the amount of deuterium in the universe, if this is done early enough, but not too early, because then we enter this whole discussion that you destroy deuterium too early and you end up with too much deuterium late. So deuterium can actually reform to its observed abundance. And moreover, if the neutrons released from deuterium dissociation can themselves play a role in the reduction of lithium-7. So we introduced this idea of borrowed neutrons instead of injected new neutrons. We also saw that especially very light particles are involved, such as in scenario B, so the light axion-like particle scenario. Non-negligible part of the parameter space are testable at intensity frontier experiments. Sorry, I forgot to say that what's testable is below this line. I think that it's relatively clear from the plot. And as a final remark, the lithium problem has been around for quite a while, but it seems that its particle physics solutions are far from being exhausted. So the next step, which is actually work in progress, is to actually provide some concrete model realizations where all of the couplings arise, if you will, in a more or less natural way. And yeah, thank you very much.
Thank you very much, Andreas, for this very cool seminar. Now we should pass to the round of questions. So please let me remind you that you can ask questions to Andreas via the Google Plus Q&A at the webinar page, and via Twitter using the hashtag LAWOP. Right. So, are there questions for the audience?
Yeah, I have a question.
Yes, go ahead, please.
Okay. So, but also I wrote it in the Q&A, but my question, did you try to, in the case of to have a cross-section that are instead of S-wave, like P-wave dominated, or something that has a strong dependence in the momentum of the particles?
So this we have not tried yet. I mean, it becomes a little bit more tricky because, yeah, in an S-wave cross-section, you just have a constant number; it remains constant, and you know, it's much simpler. No, we haven't tried that out yet, to be honest. Yeah, we actually stuck to the simplest case for this because this is just a short, if you will, presentation of the whole mechanism. We basically stuck to this S-wave scenario.
But Andreas, for instance, when you discuss these two scenarios, A and B, slide 11, you have this axion-like particle with a derivative coupling, but that will give rise to a, well, not an S wave, no?
Wait, because I think that something is a little bit wrong. Can you see the slide?
Yes.
Okay. Sorry, can you repeat? Excuse me.
So, for instance, these two scenarios, you have this ALP particle with a derivative coupling, right?
Yeah.
So that will definitely not give rise to an S wave, I think.
If I remember well, the cross-section in this case is actually a S-wave. This is not necessarily the case. Like when you have derivatives in some Lagrangian, it's not necessarily the case that that you get P-wave suppression. I mean, I can tell you that, for example, because if you take annihilation into, yeah, if you take annihilation of two dark matter particles into two gluons, for instance, through and some mediator, and you couple the mediator as S G mu nu G mu nu, for instance, you have derivatives, but still the interaction is not necessary, it's not P wave, it's just S wave dominantly.
Okay, I see.
Mm-hmm.
So I have also another question. At the very beginning, just curiosity, the slide 4, you talk about gravitational LSP and the injection, neutron injection.
Mm-hmm.
I was curious about that. I mean, how
I don't know why. Okay, sorry, because the slide is not moving for some reason. Okay, there we go.
I think what the 4th.
Yes, right here. So yeah, I mean, I'm definitely not an expert in this in these types of solutions, but you can imagine, if you will, intuitively that you can have scenarios, for instance, of mixed bino-Higgsino neutralino decaying into gravitinos, and the decay is neutralino to gravitino plus Higgs. So the Higgs then can decay hadronically. I mean, you don't just maybe I was a little bit, no, I was too crude on this point, actually. You don't just inject neutrons, you inject all sorts of hadrons in this type of scenarios, okay? But eventually, what actually helps with the lithium problem mostly, although you do affect the whole reaction chain, and so these solutions are a tiny bit involved in calculating concretely, what actually helps you with the beryllium and eventually lithium reduction are the neutrons. So I just focused on neutrons for simplicity, but generically, yes, of course, in very concrete scenarios, you do not just inject neutrons. You inject all sorts of hadrons that you can imagine: kaons, pions, protons, and everything, antimatter as well, and all that.
I see.
So yeah, I mean, if you will, just to come back to your question, one kind of standard example that I can think of is, yeah, mixed bino-Higgsino, which decays into Higgs and gravitino, and the Higgs decays as usual, hadronically, for the most.
Yeah. Thanks. So I can see another question now from the audience. It's Nicolás Rojas. He's asking if you have tried other possibilities to build a model other than with ALPS.
Yes, actually, we have some comments in the paper on that point. So in principle, the mechanism can work with all types of particles that you can imagine. You can consider vectors, you can consider scalars and not pseudoscalars. The thing works. What we felt, I mean, if you take a vector, for example, it is pretty difficult to envisage any type of model that is not extremely fine-tuned and in which you don't couple top-type quarks. So that's, if you will, the main reason that because we did consider dark. I mean, if you take, for instance, any sort of kinetic mixing, dark photon type scenario, you will not only just couple to up-type quarks, you will also couple to leptons, and that's the constraints on these type of scenarios are really stringent. Now, if we just took we have considered them. We even have calculations of all the dissociation, if you will, processes. But as concrete realizations, we just chose to focus on the ALP scenario. It's also, in some sense, a natural one, because if you consider the simple scalar Higgs-type particle, then you would have to explain a very, very...
Hello?
I cannot hear anything.
No, I think we have problem with Andreas' connection. Are you there, Andrea? Can you guys hear me?
Yeah, yes. I can hear you.
Oops.
I think
now
I think you lost me for a second, right? Yeah, sorry. I don't know where you, how much of my answer was heard.
Maybe you
We
should
lost
start
1
from
minute.
the very beginning of the presentation.
What?
No, I'm kidding.
Yeah, so no, the answer is that yes, we tried other, so I'm sorry, I might repeat myself just what I just said, but yeah, we tried vectors, we tried scalars and pseudoscalars, they all work. It's more difficult to build models with vectors and with scalars. They would be very, very unnatural, actually. So, but all of them work in principle. The basic principle remains the same. There's nothing special about ALPS, if you will.
Okay, very good.
I have a very general question. On your slide 8, you show that the solutions were quite quite stable. You could vary your parameters a lot, and you would find the solution. I'm not an expert on the problem, but here, for instance, yes, exactly. I mean,
Yeah.
you could vary a lot your cross sections and you'd still find a solution. Is there any argument that, I mean, I was expecting more of a fine-tuned solution.
I guess that's an argument in favor of the mechanism that we propose. No, it's actually, it can work for a pretty large range of, can you still hear me?
Yes, yes.
Yes, okay, thanks. It can work for a really large range of cross sections, basically, and this is exactly due to the fact that you have quite a bit of freedom to play around with the abundance of the X particles. Now, of course, if you dial up their abundance too much, you start having a problem with an effective, for instance, and things like that. So you must be careful, but at least for the ranges that we plot here, there aren't problems of this type. I mean, all of this we have checked, and it's actually, yeah, it's what you say is true. It works for a surprisingly large range of parameters, but it seems that it does. Yeah.
Okay, so.
Yeah, I have a question, maybe related with this, what you were saying before, in the sense of, because in your talk you present basically that you have this new particle that couples to quarks, but in principle you could also modify the production of element, maybe with leptons, with the production of leptons in the early universe. No, I don't know if it is possible. Like, for instance, since also at the end you mentioned the effect, some bounds from LSND, maybe this mediator couples either to neutrinos and leptons, and this lepton crashes the nucleus or the transmutation. I don't know.
So
because I mean, just because in the very beginning you mentioned that some possible solution to the problem were like a photon injection or neutron injection. I mean, or catalyst, but I didn't notice that were pointed extra leptons or I don't know, other type of variation.
I hadn't thought of injecting leptons, to be honest. I don't know which type of reaction could lead to, say, beryllium dissociation, for example, with leptons. The answer is I don't know, very honestly. For photons, I can tell you, but with leptons, I really don't know. Yeah, you've got me on that. I really have no idea. And I don't know, one thing that might actually play a role, and should play a role, is the effective number of neutrinos, for example. And the neutrino Boltzmann equations do enter BBN, and I don't know if it's possible to play around with that, for instance. That might be possible. But now, injecting electrons, for instance, this it can very well be that you get an effect which is good, but I haven't thought of it. Yeah, that's all.
So, and about this LS&D bound that you were showing in the last plot, I guess.
This is actually more sensitivity. It's projections. It's not. It's if you will, an LS&D-like experiment. That what can it say? There's a question actually, another question on the Q&A, as far as I can see.
Yes, actually, there's a question from Nicolás Rojas. So you can read it maybe. Have you considered another supersymmetric scenarios for decaying supersymmetric particles? For instance, are perturbating decays?
To be honest, in this particular work, we haven't considered any supersymmetric scenario. It's just, I mean, what I just said is simply an example of how you can have hadron injection. Are parity violating decays? I guess that could also definitely actually inject hadrons and or photons, if you will. So we haven't calculated something like that, but I am quite sure that people must have done it. I mean, in supersymmetry, people have done everything. So, especially gravitino scenarios, for instance, have been used for the lithium problem quite a bit, and I assume that if it hasn't been considered, it's definitely worth considering.
Yeah, very good. So I have another question. So in your slide 8, when you define like the parameters, so one was the ratio of the number density of X over number density of I don't remember.
Variance.
Of variance, right? Why does has to be a constant? Well, I mean, why do you expect this number to be a constant?
Sorry, no. It's actually not. It's the I explained this badly, I guess. It's the abundance of X particles at the offset of BBN, if you will.
Okay, I see.
Yeah, or if you want even more precisely, at this temperature window in which we're interested in, which beryllium production and in which beryllium production occurs. So no, eventually. Eventually, for example, since you have a finite lifetime of the X particles, typically, for instance, in scenario A, their abundance is depleted.
Mm-hmm.
So no, definitely, this is not a constant. And of course, we've taken this into account. I mean, there's a Boltzmann equation that you need to solve, and yeah. But the free parameter, if you want, is the abundance in the beginning of this whole process.
Mm-hmm. Yeah, sure. Okay, there are more questions from the audience.
Yes, sorry. So the abundance is depleted in all cases, or is there any chance that it's still around this X particle?
It can still be around. For instance, in scenario B, where the quasi-massless, if you will, case, and the particle is still around. It's just redshifted.
Right. So in principle, if you had like a deuterium experiment like SNO, would you be able to actually detect this particle?
So the only thing is that since they are extremely redshifted by today, I don't know what the observable effect would be. So if they have been redshifted to an energy of a few electron volts or something like that, then I don't know how observable that would be.
Right.
So that's the only issue I see with that. But in principle, if they were still energetic, then yeah, I mean, you have an abundance which is much larger than the baryon abundance. So although the abundance of X particles is depleted at BBN, so this should also be. I mean, it really depends on the scenario. In scenario A, we find that the mechanism works better if you have a finite lifetime. In this scenario, it means that the X particle is no longer around. In scenario B, with the massless case, then no, they are, but they're really, really, really low energy.
Okay, thank you.
So, I just have a short question in the same spirit that the one of Joel. So in principle, since they couple to quarks, down quarks, maybe also could be search this type of particles in colliders, no? Or the cross section, the production should be very small.
The cross sections are small. Yeah, the cross sections will be very, very, very small. What I don't know is if there is any type of flavor observable, for example, that could be, but it has to be some type of flavor diagonal. It cannot be charged decays, for instance. Then again, there is one issue that when you try to embed this thing in a like proper complete UV complete model and everything, of course then you get additional constraints and observables and so on and so forth. So in this case, we have completely suppressed the couplings to up quarks. It's actually a model building question to what extent you can do this, and consequently what type of other constraints you would get.
Okay, are there more questions from the audience? Okay, I have one. So when you talk about the tracers, you talk about the population 2 stars at the very beginning, but are there other tracers?
That I know of, this is considered to be the kind of the state of the art. I actually don't have a good answer to that. I guess that if ever you manage to, well, if ever you manage to observe population 3 stars, that would probably be a better tracer, but you have to see them, and you have to be able to detect something as faint as lithium, some line related to lithium, some lithium transition. So that I know of, at least for the moment, that's the latest determination. I don't know actually if for completely uncorrelated observations, I'm not really sure.
Okay, thanks. So no more questions, I see. Okay, so thank you, Andrea, very much for this very cool seminar.
Thank you very, very much.
And we thank all the viewers. So, and hope to meet you again for the next Latin America webinar on physics, which, by the way, will be in 2 weeks. We'll have Leonidas Aliaga from the College of Mary and William and Mary. He will talk about neutrinos and the Minerva experiment. So, yeah, hope to see you in 2 weeks. Thanks, Andrea.
Thanks. Bye.
Bye. Thanks.